Yeah, he's not only for that, upper limits DC can only have it's the frequency part. It's F. F exists. F gives you capacitance and inductance. At DC, F goes to zero. Capacitance and inductance goes to zero. That's what it is. So what happens on DC when you're sending in and receiving reads balanced? You have XL equal XL. Right? So even though you hold XL, you have XL inside. That's what it is. It's purely frequency. Yeah. DC frequency of zero. All that just that those equations collapse over zero.
Like a torch.
Yeah, then it's IR. That's a fun. That's what it was. But yeah, because each R is now in parallel. So total R, effective R is 1 over R, the rest of it. Oh, okay. Then will you put the mutual of it? What he's doing is doing it like the sentence. Yeah. Because they'll be watching it from Cape Town, the whole country. Because the institute live streaming.
It's always a problem to see some people in section. we need an ISCO person to show us the way.
Prof. How are you? Nice to see you. Give you one. Small, fitting. You're tall and big, but real small. James on the field. I'd like to win. He's somewhere. Oliver, I know. He's somewhere in Australia. Yeah, I'll find out. I can find out. James, Oliver. Yeah, I grew up with him. Yeah. Yeah. Nice. Small one. Small one.
Ladies and gentlemen, can we please start? I would like to call Professor Andrew Crush to welcome us. I would also like to just acknowledge the TVC, Vilagazi from VETS for research. Can you welcome Prof. Crush, please?
Good evening, ladies and gentlemen. Thank you very much, TC, for welcoming me. Ladies and gentlemen, I'll try to be brief because I told Gerda that I'm going to listen to the lecture and then I'm going to run away. So that's why I'm sitting in that side of the room. But on behalf of the University of the Witwatersrand, I would like to heartily welcome you to this 65th Bernard Prize Memorial Lecture. Now, we wanted to have the lecture much earlier in the year, normally around September, October, but I think due to some event we had this year, I don't know what it is, we had to postpone this lecture until a later date, and that date is in fact today. So it's an honor for us to also have Professor Tshilidzi Marwala from the University of Johannesburg as our guest or our speaker. Now, I don't want to enlighten you or bore you with the details of the similarities or or differences between Tshilidzi and some of my colleagues here, but I think there's one common denominator, and I can tell you later, maybe over tea, what that common denominator is. Ladies and gentlemen, the Bernard Price Memorial Lecture is a very, very important lecture on our academic calendar. In fact, I've looked around and I've asked people who are in the know on this lecture series, and I believe it's been running since 1951. So it's a long-standing lecture series, and as I pointed out, it's a very, very important lecture for Wits University. So we are, in fact, very proud to host you, although not on the Wits campus, but it would actually have been good to have you there. Dr. Bernard Price is a very important benefactor of Wits University. In fact, I know that he is an engineer, and although I'm not an engineer myself, I do have respect for engineers because I work with, okay, I won't mention names, but I have respect for engineers on the whole, and in fact the Faculty of Engineering and Built Environment at Wits University is one of the faculties that in fact reports to my office. So I have some background knowledge of the engineering profession, although I can't claim to be even a quasi-engineer. So Dr. Price, as I said, was a benefactor, and he in fact contributed and was the founding member of the Bernard Price Institute for Paleontological Research at Wits University. And that institute still, in fact, is one of our key institutes at Wits today, although it has to a certain extent also merged with other activities in paleontology, which we are having at Wits. In fact, we host the National Center for Paleontology at Wits. So you see how it has progressed with that initial investment. In fact, now we have a lot of bigger things. The memorial lecture is meant to be of scientific or engineering interest, and it's normally given by an invited guest, either from locally or normally when we have these lectures, we have a healthy attendance. And again, like tonight, we have a healthy attendance. So thank you very much for those of you who turned up to grace us with your presence here tonight. And I'm sure that the lecture which we're going to have today is going to be both enlightening, informative, and it will make us think about what is the next revolution. Not what is the next evolution or what is the next protest, but what is the next revolution. So with those few words, ladies and gentlemen, on behalf of Wits University, welcome to this memorial lecture. Thank you.
Thank you, Prof. Krausch. I would like to welcome all our guests, our members, our potential members. I would also like to welcome all our members who are not with us here. We're live streaming this. We've got 7,000 members, and I'm hoping that at least 40% of them are watching us now. Am I right? Without any delay, thank you everyone for being with us. I would like to introduce our guest speaker. As Prof has indicated, traditionally we normally have this prestigious event at Wits, but for various reasons we're having it here today, and we felt that with the guest speaker, let's make sure that we finish this series. We don't know what's going to happen in February. So hence we're having it in December, and I'm happy that the attendance is good. And I'd just like to introduce our guest speaker. Prof. Marwala was born in Venda, which is in South Africa. and is currently a Deputy Vice Chancellor, Research, Internalization, and Library at University of Johannesburg. Marwala was previously a Dean at UJ and a Professor also at UJ. And he's been a DST/NRF South Africa Research Chair of Systems Engineering at VETS. So there is some association with VETS, Andrew. And he was also a professor at UP. He is the youngest recipient of the Order of Mapungubwe, and he was the first African to be awarded the President Award for the National Research Foundation of South Africa. And he holds a Bachelor of Science in Mechanical Engineering with magna cum laude from KAIST Western Reserve University in USA. And he has a Master's of Engineering from UP and a PhD in Engineering from University of Cambridge. And he was a post-doctoral research associate at Imperial College in London. He has been a visiting professor at Harvard and Wolfson College in Cambridge. He has supervised 45 masters and 19 PhD students to completion. I was told that I must highlight this word, to completion, because he can supervise 45 and 19, but not to completion. And he holds 3 USA patents, and he has published over 300 technical papers, and including 9 books. His first book was published in 2007. You must listen to this one now. He is a fellow of SAIE, which means South African Institute of Electrical Engineers, TWAC, the World Academy of Science, the Academy of Science of South Africa, and he's also a senior member of IEEE. And currently, he's a board member at EOH. He's an independent non-executive board member. And previously, he has served as a board member at City Power and States South Africa. Can we welcome Prof, and he will tell us.
Good afternoon. Can you all hear me? Sanibonani. Thank you very much for finally organizing this Bernard Price Memorial Lecture. The first time I was supposed to speak, I kept on talking to one of the deputy vice chancellors at VETS, Tawan. I was saying that, is it safe for me to come and speak? He says, yeah. You have to be preparing your slides. And then obviously we had to cancel this lecture. But there is a saying that says, it's better late than never. So I am going to come and talk to you today about a subject that I have been thinking about for quite a while, the fourth industrial revolution, artificial intelligence, and society. I will, hopefully try to tell you some of my opinions as to what artificial intelligence is. I will talk about an aspect of artificial intelligence called optimization, and then I will go on to applications, and then I will talk about the fourth industrial revolution. In fact, I will go through all the 4 industrial revolutions leading to the 4th one, and then I will conclude this talk. This is a video from a university that I visited last year. It's called KAIST, Korean Institute of Advanced Study. So this is basically a robot that actually drives itself. You saw it driving the car. It is moving. It's not controlled. It's not remote controlled. It's actually doing it independent of its human owner. It even opens a door. Gets inside, tries its bit as an engineer, thinking a little bit. This is fast forward because it's slower than this. Thinks and then it decides to do something else. Then there are 4 drills. Then it catches one. For some mysterious reason, it pushes another one. Then it grabs. And then it drills. All are attributes that are normally in the domain of human beings. So you basically have here a machine that is trying to do what we call general intelligence, because we have been quite good at training machines to do specific tasks. But these are multiple tasks that it is doing. Now, what can we learn from this robot? Clearly, it learns. Just like human being, it is able to learn. It senses its environment. That is why it was not colliding with walls. It reacts. Well, you can say it sees, because seeing is basically visually perceiving your environment. And it can do this quite easily because it has a camera mounted on it. It was driving a car. It walks. It adapts. When it climbs a stair, it walks. But when it is traveling on a flat floor, it actually drives. It's almost human, and we will say it is artificially intelligent. But does it commit a crime? Does it fall in love? And more importantly, is it conscious? Because consciousness is one of the most controversial subjects that we hardly understand. Well, I'm reminded of an ancient saying by an anonymous person which says that nature is the best teacher. Learn from it. This is really what artificial intelligence is all about. What is artificial intelligence? Artificial, man-made intelligence, the ability to basically make sense of information beyond the obvious. Basically, it is about creating machines that are able to do sophisticated tasks that are at least in the domain of human capability. It is concerned with modeling complex systems with computational tools, and very often the algorithms are developed to mimic physiological systems such as human brain in order to carry out complicated tasks. And mathematics is obviously quite crucial in developing artificial intelligent tools. And then there is a test that was done by Alan Turing. Alan Turing was a famous computer science mathematician, British mathematician, who is probably more known for breaking the German code. I think there was a movie about him not too long ago. He says, this is called a Turing test. A machine is intelligent if when humans interact with it, they are not sure whether they are interacting with a machine or a human being. That is what is called the Turing test. For example, many of us, when we go on holidays, we have an automatic reply system. So if I interact with it once, I write an email to you, it comes back and says, I'm not available right now, please contact me later. You probably will not know whether that message came from a machine or it came from a human being. But if you write back and say, at what time should I contact you? It probably will return the same message that it returned. Then you will know. then you will know that, no, this is actually a machine. So there has to be an element of repeated interaction, because you can always make a machine that almost fools you if you interact it with it once. So far, there's not really been anything that has broken the Turing test. I keep on reading of people claiming to have broken the Turing test. There are two types of intelligence, individual versus group intelligence. I will talk about them much more in detail. Individual intelligence, you can think of it as intelligence emanating from a single brain. A brain, we know, is a system, which is quite complicated. But as a system, a single brain, we'll call it individual intelligence. Whereas group intelligence is multiple brains, whether it's a group of pigeons trying to do a certain task, or a group of lions that are trying to attack a zebra. That will be a group intelligence. So simply, on the left-hand side, that will be individual intelligence, whereas on the right-hand side, on that fish tank, it's actually a school of fish that is operating as a system. But each fish probably has its own brain. Now, one aspect of artificial intelligence is what we call learning. How do we make machines actually learn? And there are many techniques that have been developed to do that. I'm just going to talk about one that is called artificial neural networks. So on the left-hand side, you have a set of inputs that are being propagated into outputs. The inputs might actually be the price of stock today and the last 3 days, and the output will be a price of stock tomorrow. This will be a predictive system that is able to help you predict the future stock or price of stock. And this is how a neural network is actually looks like. In the middle is a much more clearer diagram. This will be supervised learning. It has sets of inputs that are being propagated into output. Where you see errors, that is what we call neurons. And neurons were actually inspired by the biological neurons that we observe in biological animals. So once you have multiple layers, this is a neural network. Exactly as I said, the neural network that I showed you there had only one single layer. This has multiple layers. You have hidden layer 1, you have hidden layer 2, you have hidden layer 3. This is what they call a deep neural networks. It's a big term now. Deep neural network is nothing but a sophisticated neural network architecture with many layers, and because of this, it is able to learn very complex things like pictures and so on. Now, how do we make neural network learn? I think this is quite important. So if you have examples of your inputs and you have examples of your outputs, this neural network says something that we call weight. In statistics, these are free parameters. This is what statisticians call free parameters. So what you do when you train a neural network, you basically identify those weights such that your ability to make an accurate prediction whenever you are given a set of inputs is maximized. And once you start talking about maximization, in mathematical terms, we call that optimization. So the mathematical framework that actually enables us to be able to make neural network learn is basically optimization. Now, optimization is a process of identifying either a maximum or a minimum point. For example, if you wanted to move from here to Sentence City, there will be an optimal path, which is the shortest distance from here to there, given the constraints, which is the fact that you can't go there on a straight line if you're driving a car. So that will be an optimum point. And to be able to identify that optimum point, we will call that process optimization. And optimization originated mainly in mathematics through calculus. In fact, Newton was the first person to formulate an optimization problem, the Newton-Raphson method. But we can learn quite a great deal from nature on how to do this optimization, especially for problems that are not easily mathematically codified. Like, for example, distances between two points might not necessarily be easily mathematically quantified. And as a result, you have an optimization technique called ant colony optimization. In fact, this ant colony optimization came out of a theory that was proposed by a South African person called Eugene Marais. Eugene Marais wrote a book called Die Ziel van die Meer, which was really the first work on understanding how ants actually do what they do. For example, the picture at the top was the picture that I took when I was in Venda, TC, in South Africa. So that was the picture. But these ants at the bottom are actually what makes that complicated structure. So Eugene Marais, I don't know which part of South Africa he was from, but I would guess he's from Limpopo, witnessed quite a great deal of this and came up with the theory of swarm intelligence. And for example, for those of you who have interacted with ants, you will see that in your houses you will see almost a straight line of ants from one point to another. And the way they work there is each one of them deposits pheromones. And, it just follows the direction in which the pheromones are stronger. And after a while, they actually identify a shortest distance from their home, from their nest to the food source, an optimization problem. And this you can codify mathematically and algorithmically. And this has been used quite extensively in scheduling problems, for example. The other one is particle swarm optimization. You can see we don't have too many pigeons in South Africa anymore. I think you probably will have to go to Trafalgar Square in London to see something like this. But they seem to be following that gentleman who is giving them seeds. Now, how do they do that? The mechanism that they use is actually quite simple. You have local best, which is individual intelligence. Each one of them has its own perspective of where the food source is. And then group intelligence, which is a group. What is the group doing? So the interplay between what it knows and what the group knows is basically what ends up making each pigeon actually find where the food source is. And this is another example of an optimization problem. And this has been used to optimize problems such as in designing power lines and so on and so forth. And the picture that I borrowed, which is a bit still, I don't know, it's almost 200 years after this theory was proposed. It's still as controversial as it was when it was proposed. This is Darwin's theory of evolution. And from this theory, we are able to come up with what we call genetic algorithm, another optimization technique. As you can see, it's just a simple genetic algorithm that is trying to replicate the picture on your right-hand side. If you allow it to go on, it actually replicates it fairly well. And again, this algorithm uses mechanism of evolution, crossover, which is mixing of genes, mutation, which is just changing genes a little bit, and reproduction. And again, we are able to use genetic algorithm to design quite a great deal of things. So we're still on the same page. Thank you very much. So I think now we have some idea of what learning is all about. We talked about neural network and how it learns. We talked about optimization, 3 optimization techniques we talked about. Now, how do we apply this? You know, when I think of application, I remember what I was once told, that knowledge only becomes education when it is used for the benefit of society. So it is all well and good to learn how all these things work, but it's even better if we can be able to put it to practical use. The first example that I will use to illustrate what AI is capable of doing, because I think we need to understand what AI is capable of doing in order for us to start engaging on what the 4th Industrial Revolution is all about. This is a project that actually I did when I was still based in Braamfontein, before I moved to Auckland Park with my students. And this is basically a program that we designed to do what is called a triage mechanism. A triage mechanism is used in hospitals, but it started in the army. So if you are a doctor in a war zone and you have 4 people injured, how do you schedule who is helped first, and then who is helped second, who is helped third, and who is helped fourth? That arrangement is called triage. So whatever criteria you might decide, if it is in a war zone, you probably want to save. Obviously, the first criteria is somebody that can be saved the fastest. Because if you can save that person the fastest, you probably can go to the second person, you know. So if the second person, they have to go on a 2-hour operation, and the other person is only a 10 minutes, you probably will have to do the 10 minutes. And other criteria. In a war situation, they even use criteria such as who is likely going to recover and go and fight the next day. Yeah. So as you can see, this is what we have done. And then genetic algorithm is there, which is where we apply it to basically prioritize who is assisted first or not. And this is actually quite powerful because this was something that used to be done by human beings, and they never actually used to do it quite right, you know, because of all sorts of limitations of human beings. And once you codify it in a machine, then it is quite useful. And this is reinforcement learning. Reinforcement learning is I think it originates from psychology. It's a neural network. You can think of it as a neural network that is able to learn case by case. So you don't give it a batch of data. You give it one data and then it learns. If it learns well, it is rewarded. If it learns badly, it is punished. And after a while, it becomes good at it, what it does. And this actually worked quite well. This is another work that I did with one of our students. It's an aerial photograph, and all you had to do was you just want to classify each part as to, and these are the classification, whether it is water, whether it is drought place, and where it can't be able to classify. And you can imagine if a person had to do it visually, it's very painful and takes quite a great deal of time. And we were able to use another type of a learning mechanism called support vector machines, which is mainly based on statistical mechanics, to basically classify this. So what we do is we take this into a domain, and then we just increase the dimension of the data until it can be linearly separated. And it works quite well. And then the work that we also did here with Mr. A.K. Mohammed and Professor John was we were trying to see whether it is possible to map. What is happening? How do I go back? You see, when things are done by human beings, they make mistakes. If somebody can come in. Okay. But the good thing is that human beings are adaptable, so they are able to correct their mistake quite quickly. Yeah. It works. The system works. Now, so if you, this is an ECG, EEG. David, is it an EEG or ECG? EEG, yeah, EEG signal, which you put in your head, and it basically, measures activities in your brain, and you move your arm, and you see whether you can be able to identify what area of the brain is actually activated. And the general idea is, is for the future when somebody loses the hand, or not even loses the hand, is probably part of a robot, and it is going to some hazardous environment. So you want to control it, while you are sitting in a safe place. So when you do this, it does that. But here we're trying to see whether we can be able to do it by controlling the mind. The concept of mind over matter is quite controversial in the scientific community. But we were able to see that movement of certain gestures actually map very well to activities in the brain. And in the future, we should be able to train people to control their brain, to be able to move prosthesis, arms, and so on and so forth. Then this is the work that I did with David. You still remember David, the work of Mr. Nadim Muhammad. This is what is called, this is also from an ECG machine. So doctors basically look at this and they have to make a diagnosis with regards to epilepsy. Of course, what we are doing here is to segment data. You extract features, you put it into a neural network. We actually used a neural network to do this, and then it is able to make a diagnosis. It is actually fairly accurate. And this should not be taken for granted, taking something that is being done by a doctor, and then you put it into a computer and it comes up with a very accurate environment. In fact, somebody did a study of radiologists. I think it was 100 radiologists who were given about 1,000 images, and then they made their diagnosis, and then the information was locked. And after 2 weeks, and these apparently were some of the best in the field, after 2 weeks, the same information was presented to the same group of people. Apparently, they changed their minds 50% of their time. And the same thing was done on an artificially intelligent machine, and it did not change its mind at all. So consistency. Well, of course, consistency is not the goal. The goal is accuracy. But it turns out that the machines were actually quite accurate. And you can imagine, and you have human beings making all these decisions, but a human being is impacted by the environment much, much more dynamically than a machine. So it is important that whatever we can be able to automate, let us automate. And this is another work that we did on internet, in a prediction of internet instability. Looking back, this is Code Red in 2001. And here we're using what is called an autoencoder. An autoencoder is basically a neural network that you train to be able to predict what it has been able to, what it has seen. Sounds a little bit awkward that you want something to tell you what you have given it. But it is doing this through some nonlinear transformation. And this is very, very important because it can be used as novelty detection. For example, if what it has seen changes, you are able to detect that this is not what it has seen before, because it now starts to fail to reproduce what it has seen. So this is called an autoencoder. And this actually worked quite well. And this work I did with Megan Russell and David Rubin. As you can see, we have a US patent here. And this was on MIT Technology Review, isn't it? And basically this is, we are mapping the movement of a tongue to what the person is saying. So if somebody loses the ability to the larynx, then, but still has a tongue, so they can be able to say what they used to say. The voice is not going to come out, but just by looking at the movement of the tongue, you are able to recreate what the person was supposed to say. I think here they call it, the MIT Technology Review, they call it a robot voice. And then the recognition of faces, this is the work that I did with Mr. Surajpal. And again, the architecture is the same. You take a picture, you make it into some form of features that goes into some classifier, which is a neural network, and is able to identify who the person is. So, and then the other thing that it does is able to estimate missing data. This is a book that we wrote on how you can be able to use artificial intelligence to basically predict missing information. Again, we use an autoencoder which is able to replicate what it has seen. And if one of the variable is missing, you basically search for the variable that is missing until it is able to reproduce everything that it has seen. And this is another area that I have become very interested in, the concept of making rational decisions. I think when somebody is asked one question today and in 2 weeks' time and they give 2 different answers, I don't think that is rational. I think it's actually irrational. And we have spent quite a great deal of time trying to understand what causality is. Because causality is not correlation. And much of what is detected, of course, within causality, there is correlation. It's for 2 things to cause one another, there has to be, if you observe them, there has to be some correlation. But that is not sufficient. And the only way you can be able to detect causality, I think they call it the transmission theory of causality, is there has to be a flow of information from the cause to the effect. And when you are detecting causality, you are basically detecting that flow of information from the cause to the effect. And you can, these books are all on Amazon, and I encourage you to buy them. So this is the work that we did with Evan Hewitt. In fact, it made it to the front page of New Scientist, where we actually proved we were able to demonstrate that a computer can actually, on its own, learn how to bluff. And I'm not bluffing. And as you can see here, Hewitt and Tshilidzi, maybe you just forget the Witwatersrand part here, because the 2 gentlemen now are at the University of Johannesburg. But again, these are other things that we normally see human beings doing, and the computer can be able to do this. My grandmother always told me that every object has something to say we should learn to listen and interpret its message. My grandmother used to make clay pots. So, and making clay pots in a village in Limpopo is not as simple as we think it is. You know, she will do a nice shape, and after that she has to put it on a fan. In fact, it first goes to the sun so that it can dry, because if you take it to the furnace directly, it is going to crack. And then after that, you take it to the furnace. It's almost, you can even see it is red. And then after that, she will knock it and listen to it, and she say, "My grandson, this is a good one," and so on and so forth. But she was doing that by listening to what it has to say. And now we can do the same thing. Obviously, instead of using an ear, as my grandmother used to do, you can basically use sophisticated, accelerometers and so on and so forth. And you are able then to be able to tell whether a structure is good or bad, or the structure is about to crack or not crack, and so on and so forth. And this is important. This is a picture of a bridge in Sandton. You all remember when this bridge collapsed. Of course, if you had wires, if you had signals coming out of that bridge, you would definitely would have been able to predict it before it actually existed. Of course, there are the economic part of this, you know. So this is another work that we spend a lot of time doing. AI can monitor the condition of structures, and we actually wrote a book published by Springer on this work, both in mechanical and electrical systems, and so on and so forth. And then the other work that we have done is, this is a finite element model. Why do we need a finite element model? We need a finite element model so that we can design better cars or any other structure. And to design it on a computer is better than designing it physically, because you can test all sorts of properties. How thickness here and so on and so forth. Instead of building it, you can just do it on a computer. But unfortunately, what you get on a computer is not necessarily what you measure in reality. So the whole discipline of making finite element models better predict or reflect reality is what is called finite element updating. And we have spent a lot of time working on how we can use computational intelligence tools, because ultimately it's an optimization problem. Because at the end of the day, you are basically identifying the set of parameters that you are not sure about, such that the distance between the prediction of your model and your measurements are minimized. And you can also, and one of the problems that you encounter when you use standard optimization techniques is that you have multiple solutions, and each solution is not necessarily the correct one. And because of that, you can use Bayesian statistics, which is another book that I wrote with Ilyas. Ilyas, are you here? Ilyas is from the northern part of, is from Algeria, and we co-wrote a book together on how we are able to do this. And then another work that we have been working on is how do we use artificial intelligence to basically understand the economy, to predict the stock market. I remember one of my students coming to me and saying that, yes, I have come up with an algorithm that is able to predict the stock market. But unfortunately, it predicts 1 day late. I said, no. But that is a lookup table, you know. That was Gareth Sitat, who came to tell me that. But we have spent a lot of time doing this work on how to use artificial intelligence to understand the economy. This is the work that I did with Monica Lagazio from Italy on how to use artificial intelligence to predict interstate conflict. This has now been translated into a Chinese Mandarin by the Chinese Defense Industry Press, you know, and there were fixed copies that were published and that were printed, and it was quite exciting, especially the royalties. And then the other work that we have actually been working on now is, economic theory has been crafted under the assumption that the principal agent in the decision-making process is a human being. Now, more than ever before, much of the decision-making are actually being made by machines. Now, if that is the case, what happens to the whole concept of economic theory, whether it is the principle of demand and supply, whether it is the principle of rational expectation or theory of rational choice, and so on and so forth. So we have been quite preoccupied on doing that. And one of the theories that was proposed by Tshilidzi was the theory of, in fact, he won a Nobel Prize for this, of information asymmetry. What he basically said was that information asymmetry means, if I'm the customer, I don't know about the product that somebody is selling than the person who is selling it. And they use the concept of a used car salesman where one person is selling good cars, another one is selling bad cars, but you don't know which one is which. That because the person who is selling bad cars is probably more willing to offer a discount than the person who is selling good cars, it actually drives the person who is selling good cars out of the market. And as a result, information asymmetry distorts the market. That is the information asymmetry. Now, what happens when we remove human beings in that transaction? And it is an artificially intelligent buyer who can go and search into the internet. What we found, and this is actually being taught at Cornell University, and I got this from their lecture notes, and you can see we were being quoted. They were saying that we discovered that artificial intelligence can greatly reduce the degree of information asymmetry. Quite straightforward, because now it's not a human being, and they can be able to search much more. But we also found that it is able to enhance efficiency of trades, but it decreases the volume of trades, which is a little bit counterintuitive. Why does it decrease the volume of trades? The reason is because you buy something because of information asymmetry. If you have 1,000 rands and you want to buy, a phone, the person will only sell you if he thinks your 1,000 rand is worth more than the phone. And you will buy it because you think that the phone is worth more than the 1,000. So when you reduce that degree of information asymmetry, you actually reduce the volume of trade. And this is, I picked up on a German website where they were talking about the concept of information asymmetry and the theory of efficient market hypothesis. What it is basically saying here, it is saying that, for those who read German, you probably can see what it says. It says that artificial intelligent traders make markets more efficient. And it has all sorts of implications on behavioral economics, which is based on the fact that the principal agent is actually a human being. And in fact, there are lots of interesting studies that you can do as to how all this actually mix together. Now, we now understand that artificial intelligence can actually do a lot of things that we do. How does it link to the fourth industrial revolution? Before I talk about that, I will just talk about the industrial revolution and the respective DNA. The first industrial revolution happened in 1784, mysteriously in some island, not even in mainland Europe. It's actually quite extraordinary, because statistically it should have happened certainly in India, because that is where the population density was the highest. And perhaps China. China is geographically bigger, and so on and so forth. But it happened in this unknown island. And why did it happen there? Of course, it gave us steam engines, trains, mechanical machines for production. I think its DNA was Newton's laws of motion, because from that moment we were able to predict how things are going to move. And if we're able to do that, then we can be able to design things. Of course, it was just not the DNA was actually the Newton's law of motion. That's my thinking. The second industrial revolution, which gave us assembly line, electricity, I think its DNA was electromagnetism, especially Faraday and Maxwell. Very, very key. Because, of course, you all know that when you put a conductor next to a magnet and you move the conductor, you get electricity. Very important. If you put electricity through a conductor, it moves. And because of that, you get an electric motor. And the electric motor gave you the assembly line. So that was the DNA of the second industrial revolution. Without these two gentlemen, of course somebody else, it would have been somebody else. Maybe Vilakazi and but that was, of course we do know that electromagnetism was actually what led to Einstein's theory of relativity. To basically map Maxwell's equations with Newtonian mechanics. And then the third industrial revolution was obviously a transistor. That is not, when you were in primary school, they say something conducts electricity or it does not conduct electricity. When you were able to find material which conduct electricity under certain conditions, then you were on your way to getting a transistor. That was the third industrial revolution. Now, the fourth industrial revolution, I think artificial intelligence is the DNA. I might be biased, but that is actually what everybody is saying. And from now henceforth, information becomes a huge currency. Issues such as big data, cyber security, and so on and so forth. And I think the DNA was basically Alan Turing's ideas, of man and machine. So in the 50s, took a long time to take off, but I think, and this is very important for us that, little things, these were big things, have huge impact on the evolution of history. And what are we going to see in this fourth industrial revolution? We're going to see a reduction in the participation of people in the world of work. Bill Gates says that almost 80% of the jobs that exist today will not exist in 50 years' time. And he says quite a great deal of what do we do for us as educators in order to prepare young people for this era. Well, there is a Japanese proverb. It sounds very modern proverb, but it's quite instructive. It is inhumane to expect that which can be done by a machine to be done by a human being. So automation is not the enemy. We just have to find ways of... and these are the sort of skills that we are actually training people for in 2015. And these are the skills. This is according to the World Economic Forum. You can see in 2020. Now in 2050, preparing people to live in this fourth industrial revolution, what do we do? I think critical thinking skills are key. I think skills that require human interaction are key. For example, if you are going to go to a doctor to find the outcome of some investigation that was done, you probably will be at ease interacting with a human being than a machine, isn't it, Tina? Because there are empathy, for example. We can't be able to build robots that can be able to show emotions. We can try, but then emotional intelligence, judgment, very, very important. Many of the decision making that are mechanical, they are going to be more and more be made by machines. But I think there's still an element of judgment that makes a human being such a crucial person. When people are, fighting, the person can be able to look at the expression in their faces and be able to diffuse the situation much, much better than a machine. Negotiation and cognitive capabilities. Aristotle actually foretold this era that we are living in. He said, the end of labor is to gain leisure. I think that is quite instructive for us. Now, what is the implication of the fourth industrial revolution for us on education? I think the bricks and mortar are going to become less important. I can see people shaking their heads already. Because online blended learning enabled by natural language processing will become very, very key. The transportation, it's already here. Automated cars, trucks, buses, airplanes. Most of the aeroplanes now, or most of the pilots in aeroplanes are just spectators rather than active participants in the movement of. The cost of goods will drop significantly. Robots do not come together and form a COSATO. And you don't feel bad when you make them work for 24 hours. I think the structure of economy will change drastically. Those with means to acquire all these machines that they're going to use for production will become wealthier and wealthier. And we'll have to rethink on how we're going to deal with that. Of course, new types of jobs are going to emerge. I think safety and security, not too long ago, I heard that there was a standoff in Texas, and they used a robot to actually, not diffuse the situation because there were casualties there, but certainly robotic cops in medical health, medical devices, automated diagnosis. I just spent a time with Samsung in South Korea. They are putting sensors in all sorts of places that I never thought of, in belts, where they are measuring all sorts of vital characteristics and sending the information to a doctor, and so on, in watches, in wearable clothes, and so on and so forth. So it will obviously revolutionize that aspect of life. I don't have sound here, but this is from iRobot, when they were arguing about whether robots can kill or not. Now, what are the implications of all this, especially on the ethical side? How do we ensure that machines do not harm humans? What ethical framework will guide the decision-making of an intelligent machine? For example, faced with an accident, which life should a self-driving car save? That of the passenger, owner of the car, or that of the group of pedestrians, if you have to choose one? If a car can be able to make such a decision, how does a machine avoid statistical bias, which could have dire consequences? For example, AI in mortgage applications, which is actually quite used now. I think the morality of machines is something that we need to also start thinking about. The ability to act in a manner that is considerable towards humans and possibly other machines. There was a British philosopher who came up with the theory of the maximizer. They call it greatest happiness to the greatest number of people. Utilitarianism. Is that the theory that we need to use in order to embed in our machines? If we are using utilitarianism, this will be a very easy answer to solve. because you have one person in the car, you have a group of pedestrians. It's clear that if one has to go, it will have to be a passenger. But that is utilitarianism, because you are going to result with the greatest amount of happiness of 7 people here as opposed to a happiness of 1 person. So those are some of the things that we will need to think about. And I think this is the problem that we actually... Thank you very much.
Thank you, Prof. I would like to call Viv, our past president, to say the vote of thanks.
Thank you, Mr. President. Colleagues, friends, ladies and gentlemen, this is the 65th BP lecture. And if you do the arithmetic on the list in your programs, you'll find that we haven't missed a year yet. Almost, but not yet. Now, the BP lectures, if you look at the subjects, in fact, have tracked key technologies and new science. And, in fact, have often behaved as a precursor to promised and actual breakthroughs. This evening is no different. What we've heard is that we're on the cusp of a promised new age, and that this cusp, or this revolution, or this promised new age is going to revolutionize society and change our lives and our children's lives. Now, the thing about this is that with this change, we have heard that there are going to be challenges. On the one hand, people are going to be replaced executing mundane tasks. And I was really intrigued to find out that 70% of current work will not exist in 50 years. I'm waiting for that time. On the other hand, the same technology and the same science is now going to help us with education so that we will end up with a much more educated society. Tshilidzi, you've now joined a list of esteemed speakers, of BP lecturers, and I wish to congratulate you on that. Thank you for your time, thank you for your insight, thank you for your lecture this evening. And if I could ask you just to come forward and accept a small token of our gratitude. Thank you so much.
Thank you, Viv. I need to adjust this. Thank you, Viv. Thank you, Prof, and your family. I was watching who's taking the present. I can see Prof. Junior is taking the present. And I would like to thank everyone who has attended this 65th BP lecture. And thank you very much. I invite you now to join us for refreshment. Thank you.
That isn't screwed on the security. No, that's his. This is well with the